Well, so with no further ado, Matt VandenBrink. Thank you for your
Okay,
time.
thank you. My background has been with Allen Test Products, and I learned a tremendous amount of things during the time that I worked for them for 40 years. And my job is now, of course, to share that information with you, but not only what happened years ago, but also what happened today. So we've been trying to keep up to date. So my specialty is scope pattern interpretation. So I'm going to start out right away with this. What do you think we see on the screen? What would you diagnose from this scope pattern?
Plug wires on.
Bad plug wire. The word resistance. Okay? Resistance is, we either have an open or we have a short, and anything in between is resistance. Alright? So resistance can be a variable from anywhere gray to black. So when we talk about resistance, as long as there's no current flow, resistance has no effect. Do you agree with that? Okay. As long as the voltage keeps on climbing and climbing and climbing, we are not having any current flow, right? It's in the process of coming up to an ionization point, and not until that happens, that's when actually a spark occurs. So in other words, when you talk about resistance, that is not resistance. That is. You see the difference? Okay, here there is current flow. Right? The spark actually occurs, it finds the molecules of hydrocarbon, and that is the conductor. Until it runs out of hydrocarbon, and no longer do we have any current flow, now we have a secondary, or actually the residual energy that's left over. That's not zero at this point. There's still energy left. And that is absorbed in oscillations. Okay, so that's basically what we see. So when we say resistance, when we talk about kV, resistance has no effect. Do we agree with that? All right, so we heard there that it was maybe a spark plug wire. Well, I disagree with you. That is a lean injector. Now, why would it be a lean injector? You see, when we say a spark plug wire, then we really don't know whether spark plug wire, whether it is an intake manifold leak or whether it's a lean injector, unless we know the condition. So what's the difference between a spark plug wire and a lean injector? Is the spark internal or external? And how can it tell whether it's internal or external? Can anybody tell me? This is actually absence of hydrocarbon. Because there's a conductor here that's hydrocarbon, there's absence of hydrocarbon. And if there's a bad wire, yes, that's absence of hydrocarbon. But so is a lean injector. How can I tell the difference? I need to know. Because I need to know what I'm going to do next. Replace a plug wire? No, it didn't work. So therefore replace an injector? Yeah, maybe that's the way to do it. That's not the way to do it. But instantaneously we should know. No idea? What will happen if I rev it up and it is changing? Then I know it is internal, because the spark plug wire doesn't get bigger and smaller, right? So if that remains the same, that is external. It's not affected by RPM or fuel or compression, right? So the first thing I need to know when I look at a scope pattern, under what condition are we having it? And therefore the most important thing is, now that we look at a scope pattern and say, yeah, it looks pretty good, I don't think there's anything wrong with the car. Hey, at idle we don't know. We don't know what is wrong with it until we rev it up and slow it down. Now if I would rev it up and slow it down, what do I know from just that action? Go to higher RPM and go down to low RPM. What do I know from that? Come on, let's think it out, okay? Logically.
Injectors,
are we looking at components? That the scope doesn't know doesn't know automotive. The scope doesn't know automotive. All that it knows is voltage variation and time. So don't ask me that the scope is telling me something. I interpret something. what variation of voltage and time is. That's an interpretation. but we don't throw a part at that, right? So consequently, what we're saying here is there's a whole bunch of other things that actually enter into the picture. And we're going to open it up. And we're going to do that with logical thinking. And what we're going to do tonight is I want you to throw away anything that you have in a database about scope patterns. Okay? Forget it. Throw it away. Because after tonight, you're going to reason it out and logically deduct why something happened in the combustion chamber. And then you don't need scope patterns, because let's face it, there are no two scope patterns the same. There are no two people alike. Oh, sure, they all have two legs and two hands and a nose and two ears and so on. If that is the same, right, then we are not really communicating. Because what we are looking for is the difference, and knowing that what are the symptoms, what makes something happen, and what doesn't happen. So I'm going to go very much bit to the basis, and let's just start at this. Okay? Let's look at the four-stroke cycle. Give me some answers. What happened first? Come on. Intake, right. What next? Okay, compression. Next. Oh, power. Is some power that's something we can fix, or would we say spark or ignition? Ignition we can fix, right? Power is all of it. So yes, it is a power stroke. But you see, when we think about it as a person who repairs things, it's better that we think about ignition. Okay, when we go to that stroke. Okay, let's call it ignition, but power is a good answer too. Next is exhaust. Now here are our 4 steps. What do we really know about all of that? So let's just rehearse that for a minute. Let's see now, it's not enough to know how it works, we also need to know, and we must understand what causes failure and how to analyze it. And that's the important part. So let's look at this. To be successful, it is essential to understand logical analysis. What is the objective? What may inhibit that objective, right? What starts and completes it, and you name it. So we go down the list, and we put things there, how it works and why it works that way. Now, purposely, I've given you no handout. And the reason that I give you no handout is because the minute you write down, you're not watching me. And you're not looking at that, right? And therefore you're missing something. And then I got questions asked that I just answered. Okay? So if you write things down, you're definitely missing something. Now I have written everything down for you on the disk, word for word. I see that some pencils are going to go down. But word for word is there. Okay? You can always rehearse it. What I want you to do is relax, absorb. And when you absorb, think it out. Because I'm going to ask you a lot of questions. And when I ask you questions, then come up with an answer. There's not such a thing as a dumb answer. There's what is dumb if you walk out of here without knowing the answer. That is dumb. So let's ask the questions and let's look at that. Intake. Let's explore. What is the objective? Think about it. What is the objective of the intake? Bringing the fuel in the combustion chamber. Does the intake brings the fuel in the combustion chamber? Where does the intake grabs the fuel and puts it in the combustion chamber? Creates a mixture in the combustion. Air-fuel ratio. It mixes it in the intake manifold. Is that what it does? All right. Okay, if you were an engineer and you have to make the most perfect intake manifold, what would you design?
Direct injection with the piston.
You see now, we are talking about now thinking about something different, because now we are looking at what makes a good intake and what makes a bad intake. What makes a defective intake and what causes a problem with intake. Pardon me?
Balance air to all the cylinders and blending the fuel.
In order to do that, what do we need? In order to make everything just perfect, what do we need? I'm going to give you the answer. And I'm going to ask you, did you think about that? What is the objective? The objective is to maximize valve opening for minimum restriction. Simple answer. But you see, if there's anything wrong with the intake, then it is restriction. Why is that intake valve so much bigger than the exhaust valve?
Because intake is under vacuum. You need more.
It's harder to inhale fuel than to let it out. In other words, the same thing as it is harder to put air in a tire than to let it out. Obviously. You know, if something has a leak and it's gone, we don't have to do anything in order to do that. Right? The same thing when you have pressure here and you open an opening, there it goes. But the intake, now you have to force it kind of in. So therefore, what is the most important factor on the intake, at what speed, under what condition, and what driving condition? Control position is way up here, right?
Well, yeah.
Okay. What's the most important?
Down the highway, 30 miles and 40 miles an hour.
At 40 miles an hour. Okay, so then it's not at idle. Right, the big intake valve was not there at idle. As a matter of fact, if it was smaller, it would have run a little bit better at idle. But because it's so big and there's so much valve lift, if there was valve lift, it's, you know, that is how a race car works. So we do know now that when there is a problem, it's so under load. So therefore, if we do any testing, we don't do that at idle. If we wanted to look at restriction, then we're not going to look at a scope pattern at idle. We are looking at under load, at least at high speed. Okay? So consequently, what we are doing here is, when we do a cylinder balance test, forget the idle, go to high speed and see what the difference is between low speed and high speed. And if that is lesser performance at high speed than low speed, that could be a restriction. It's a matter of fact. Anything that gives me worse condition at high speed or under load than it happened at idle is a restriction of some kind. It can be an intake restriction. It can be an exhaust restriction. It can be a fuel injector restriction. It can be an electrical restriction. Right? Anything that is happening under load or misfiring or missing under load, that is always related to restriction. Now, there's half of our battle of diagnosing. By knowing that. Right? So it always is a restriction, and we're going to go in details there. Okay, now, let's go to the next step. What may inhibit that objective? The objective was to maximize the valve opening for minimum restriction, right? What may inhibit that opening, that restriction?
Build-up on the valve.
Okay. Worn cam lobe, collapsed lifter, carbon buildup on the valve stem, anything along that line. That are possibilities. And if that are possibilities, then I need to know also how to diagnose which is which. Right? I'm not going to tear the engine apart to find out which is which. So we want to diagnose that. So let's just look at that for a minute, and let's going to say, what are we going to do now? How would we look at it with a scope? Do you think that a scope can find out what the problem is? That is a restriction. I'm talking about intake restriction. An intake restriction could be anything of valve lifts, right? So in other words, it's not opening far enough. That would be collapsed lifter, worn cam lobe, or even carbon buildup, that the opening is not big enough, right? Any of that. Any idea? Have you ever seen it on a scope that you say, oh yeah, I know how that is? Okay, did you see there's a scope arrow? Now I'm going to find with and you have that disc, by the way. Okay, what I'm going to do is I'm going to find my little arrow by just going back and forth here with my mouse, and I'm going to go to scope and I'm going to click on there. What is the scope telling us? Linda would say, there is a goober, and I know which one it is, number 3. Cylinder number 3, 4 in firing order. That's the goober. Now that's the first objective reaction that we have. And there's nothing wrong with it. By observing that there is a difference between that one and the others. What it is, that's your next step. All right? Let's give it some clues. And here's the clue. Number 1 is, if I want to diagnose this guy, I need to know what this guy does. I need to know what a good one is before I can really say what a bad one is. If you have never hooked up a scope or have not hooked up a scope for the last 3 months and only take the scope out of the corner because you worked on the engine for 3 days and you finally gave up, you say, let's see what the scope says. You are out of luck, man, because you have no idea what a good one looks like. Right? You forgot all about it. And then you go back to your database. 250 pages. Is it this one? No. It's this one? No. Is it this one? Maybe. Maybe. No. No. Let's go to the next one. Can you imagine the time consuming? Let's reason it out. Let's go step by step and see, why do I think that this is an intake manifold problem or a intake restriction? All right. Clue number 1. Look at that one. Okay, clues. Correct air-fuel ratio at the start. You see, the voltage required to fire the plug, it ionizes, it fires across. There, and there, and there, and there, and all over the place, a correct air-fuel ratio when it started. All right? Next step. Not enough hydrocarbon to maintain firing. Right? All of a sudden it stopped firing. The conductor is gone. Wow, that's high resistance. Do you see that? You see, it doesn't see the molecules of fuel anymore. Because carbon is a conductor. We know that carbon is a conductor, right? And if you don't believe it, take a pencil, take the rubber off, put the finger on the end of the lead, and put it at a spark plug. And you'll know that that is a conductor. That's carbon. Right? So therefore we wanted to see here, why is that resistance all of a sudden going higher? Now that could be, of course, that I have a lean mixture, right? That could be an injector problem, right? Could it?
No, because it started off higher.
Okay, it's not a lean mixture. We have already made that conclusion, right? Lower kV demand. And why is it the lower kV demand? Is there any reason? Pardon me?
Doesn't have enough molecules to create the conduct, the end of the result.
I like the word conductivity. I don't like the word resistance, because a resistance I can't measure with an ohm meter. But conductivity is actually what it is. Conductivity is actually, it is conducting, so the opposite of resistance. All right? If I have lesser amount of volume, there is lesser amount of air and fuel, then the result is that I also have lesser compression. What more proof do I need? See? Lower compression because less volume. Does that make sense? It got to make sense. All right? It got to be logical. So basically what I've done here is say, yes, I have concluded it's a worn canlobe. Well, you can say, I'm from Missouri. I don't believe that. Prove it to me. Now let's prove something that I just said a little bit while ago. Right? And we do that with a cylinder balance test. Power performance test. Low versus high. If I do a low performance test, it's okay. And at high speed, it doesn't, no power. Why is that?
So high speed, the cylinder can't fill.
Okay.
At low speed, it can, so it doesn't demand as much.
It's not the demand. It can't. It can't. It can't get there quick enough. Okay, at low speed, the piston goes down. I need a small opening to inhale the whole thing long full. But at high speed, resistance has a greater effect when there is more flow. Do we agree with that statement? Resistance has... Can you give me an example, another example, of something that daily you run into? You can prove it down every day. Fuel filter. If I have a fuel filter that's 80% restricted, does it affect my idle? Maybe not even high speed, but boy, try to climb the hill. You haven't got it. That resistance has only effect, or really has the greatest effect, you know, when the demand is the greatest. Same thing with fuel. The same thing with airflow or with exhaust. Does that make sense? All right then. So now by cylinder balance test, now I have really made the proof. Now could it possibly be that could be a, let's say, a burn valve? It inhaled a little bit, but you know, while when it was pumping up, it threw some of that hydrocarbon out of the tailpipe, and that's the reason why I have lesser, and that's also the reason why I have a lower KV. Right? So that whole theory could be totally wrong. Agreed? What made it right? What made that statement right? This. If I have a burned valve, that means now that I have at a low speed, right, it comes to compression, I push all that hydrocarbon out before actually it fires. But at high speed, I don't give it a chance to leak out. There's enough valve overlap that would actually allow it to leak out, right? At 60 miles an hour, I would never know whether I have a burned valve. At idle, I certainly will. So if I do a cylinder balance test at low speed, it's a dead engine or a dead cylinder. But when I do it at high speed, I wouldn't even know the difference. You see the difference? I've proven a point. So anytime when we do any diagnosis, prove it to me. You say to yourself, prove it. Don't believe it, prove it. And you can prove it by tearing it apart. Yeah, now I proved it, yes, but it's 2 hours work. You don't want to do that. Well, maybe you do it in a half an hour, but I would take it in 3 hours because I don't do it every day. You see what it is we have to prove to ourselves we are correct. And we need to know, therefore, what resistance, what the effect is, how it is actually benefiting with high speed and low speed, etc. So any diagnosis that we do is always speed and load related. Or
Shouldn't that be carbon on the back of the intake?
carbon on the back of the intake valve. Yeah. Right.
Could that be the same?
Right. It would be slightly different. It would be more turbulence, okay? It would be more of a turbulence created. In other words, it would not be such a direct shut-off, where this is perfect and that is not, but very close. The effect is the same. A valve lifter effect is the same, right? Now, usually there are some other things that we can tell it is a lifter or not, right? By a noise. So you see there are other things that will tell us, yes, we do have a restriction, yes, we did prove it out, and yes, it does affect it, but there's another thing, and it is the noise that you can say, hey, maybe it is not a worn condition, but maybe it's a lifter problem. Or maybe it comes and goes.
You said a burnt valve would give the same looking pattern?
Pardon me?
You said a burnt valve would give the same...
No.
Oh, okay, I was gonna say, 'cause I would think that would be
The scope pattern would be different. But you can reason it out. You can say that, this could be. No, the scope pattern would be different.
That's what I was thinking it would be, because you would have a lower pressure.
Yeah,
you would
okay.
drop down.
But somebody could say, oh yeah, it is lesser hydrocarbon. That could be because it already has escaped. Right? But this is the proof of the pudding, basically. Now later on we're going to see what difference there is in a scope pattern when it is leaky exhaust, because that starts from the beginning. We never have a good one at the start. Okay? A leaky valve. It's already pushing it out before there even is a spark. Alright? Now notice now that there's an arrow there, and with that arrow I get back to where I was. I'm now at slide 115 or so, and now if you would take this back here and click on here, that's where we were. Okay, so that's how I bring it back. I wanted to express that so that you know where that arrow is for. All right? And once you click on it a few times, you get all mixed up. Maybe you have to start all over again. But anyway, here we are. We are talking about the intake. Now then, what customer complaint may trigger us to suspect a possible intake restriction on one cylinder or common to all cylinders? That cylinder, it's missing. It's a misfire. Right, underload. Okay, underload. Okay, do you see the logical reasoning that we wanted to do in order to actually come to a conclusion? Now let's look at loss of compression. Okay, pistons in top position. Possible causes, what are they? Let's name them. Valve seating. Anything else?
Ring seating.
Okay, head gasket. Spark plug seating, possibly. Worn rings. Right, valve spring. Oops, valve spring? Yeah? What has to be wrong with a valve spring? A broken valve spring or a weak valve spring? Or is there no difference?
Either one.
Well, it's the same replacement basically. You know. Okay, so let's do something. Let's say now, what is a diagnostic media that I can have? And anything goes. Eyes, ears, noise, whatever. Scope analysis, visual inspection, sound, noise, power, performance. If I have a valve seating problem, how can I find out? You agree with the scope? Yeah. Anything else in that list? Power, performance? Yeah. Anything else? Okay, I'll give you number 3 too. Okay. Sound or noise? Pop out a tailpipe, whatever. But there are symptoms, there are things that you are familiar with that will add to your diagnosis, right? That should not be the only one or the only conclusive one. So let's look at the head gaskets. Okay, pretty well all of them, right? Anywhere from a bubbly radiator losing antifreeze and white tailpipe smoke, you know, and so you name it. There's a whole bunch of things that gives you that idea, but the scope is good, the good reason, and also power performance will tell us there's a problem. Spark plug seating. 1 of 4 definitely, but 3 I can may hear that hiss. Psst, 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 every time when there's, okay, it's seating. Worn rings. 1 of 4. You agree with that? Or can I see something? Hear something? I could have burnt oil, you know, if it is real bad. But that's not a diagnosis, that's an adding on to your diagnosis. It substantiates.
When you have the blow, by visual, I was going to say.
Yeah,
blow
right.
by PCB.
Yes, right. Blow by, typically, that's, yeah, right. Okay, valve spring. 1 of 4, right? Now, let's just look at a scope analysis. Let's just see what we have in scope analysis. We have A and D with the scope and E. Let's just go to E. Any idea how you can tell whether you have a broken valve spring? Come on. Where's my arrow? Oh, here we are. Okay, let's go to here. Does that look like a broken valve spring? Well, let's look at this way. Let's just look what we have. Hold the RPM at 2000 RPM and quickly release the throttle. Nobody does that, therefore you don't find it. The kV demand should snap back to compression kV on deceleration to idle. Bingo, that was a good valve, right? Brought it right back. kV is right there. Except for one, which is delayed. So, a valve spring controls the valve closing. A weak or broken valve spring may cause delay in closing. I was over at a place once and the guy worked for 3 days on this car. The owner called me and he said, would you mind to help him out? And I went over there and he was very belligerent to me because he did not want the boss to call me. You know, he was a good mechanic and he really was. He was a good tech. And he missed it completely. And so what I did is I looked at the scope pattern at idle, perfect. The only thing that I saw was a little bit hash, not really much, but a little bit hash. Now he says it was this cylinder, and I said I don't think so, I think it's that one. Okay? So we disagreed right from the point, you know, and that was embarrassing for him. So what I did is I revved it up to high speed and decelerated. And my kV went all up except the one, to just a fraction later. Now just imagine what a fraction later does. That fraction later allows more of that hydrocarbon that was just inhaled to push out in the tailpipe. And there it is, hydrocarbon in the tailpipe. And therefore there's a lesser volume. The minute that I have the lesser volume of, let's say, less than half of that, that's a dead cylinder. I'll show you that later, I'll prove it. It's not that I got to have 0 hydrocarbon in order to have a dead cylinder. If I have 50% of the hydrocarbon needed, I have a dead cylinder. Or less.
Go to the 2000 and release it?
Yes, I go to 2000, okay, hold it steady there, and take my hand away, right? Let it come back by itself. And look at the KV. Beautiful way of telling, okay? Because you see, a broken valve spring usually comes back to seating. If I do, that's not my phone, is it? Okay. If I have a condition, let's say that I do a compression test, I can miss it completely with a compression test. Because compression is there. Okay, it pushes it closed. Now maybe that all the other cylinders, 1, 2, 3, 4, it is at 120. And this was 1, 2, 3, 4, 5, and now it is at 120. If I would count properly, then I could see it. Yes?
If you're doing this, would you have to disable the idle speed control motor so that it doesn't affect that deceleration?
Yes, you ought to do that. Yeah, right. If that isn't slowing down, then yes, there's a good point that you make there. But the idea is to release it in a snap. All right?
You could start at 3,000.
Pardon me?
You could start at 3,000.
Yes, sure. Because, you know, it takes very little on deceleration for that valve to come right close. Okay? Now, let me ask you now this question. Did we say that the KV goes down at higher speed? Why is that?
Reduce volumetric efficiency, you get less air.
Air. I'm here sitting at 12 kV, and I rev it up, and the KV goes down, and I let the accelerator go, and it goes back up. Why is that?
No fuel on D-cell.
More fuel, or less fuel on D-cell.
And
The injectors are being turned off on D-cell.
Inefficiency at idle.
Efficiency at idle.
Engine's very inefficient at idle, it requires more kV to fire the mixture. Whereas at higher RPMs, the engine's more efficient.
At higher RPM, the engine is more efficient.
Less restriction,
What kind of restriction? Air restriction?
air restriction, I guess the throttle plate, you can open up the throttle plate. So it's less air restriction.
Are you still thinking, or are we guessing? Are you proving something?
I'm telling you less air restriction.
Okay, all right. I like the questions.
From the amount of fuel in the cylinder?
No. No. The voltage required to fire the plug is determined by a spark gap. And then under compression, the KV goes up. What happened when I'm at idle or at 2000 RPM, when my spark occurs? I'm at 35 degrees before top dead center. Is that high compression? By revving it up, what does it tell me? That I had compression to start with, and also that my timing advance is working. Boy, how stupid for me not to rev it up. There are two things I know.
So there's less compression in the cylinder when the spark event starts,
Sure.
when you're revving it up.
Absolutely. Before top dead center, the piston is not there yet, right? I'm so many degrees before top dead center. Top dead center is maximum compression. Now we need to remember that, because later on we're going to do some testing while cranking.
Well, I'm sorry for being confused on this.
Okay.
But when I snap throttle, now basically, when I go to high load, shouldn't the timing retard at high load? The RPM didn't go up, just the load went up.
Okay.
Right?
Okay.
So,
okay. You're
in
right.
other words, when I snap the throttle, I see the KV go up.
Yeah.
All right, now, if I rev the engine way up and suddenly release the throttle, I create a high vacuum, and at that time, usually I'd see the KV drop way down.
Yeah.
Is that correct?
Okay. You're right. I was not talking about a snap test at this point.
Okay.
I was talking about high speed or low speed.
All right, I'm sorry.
Okay? No, he made an excellent point. He was talking about a snap test. We're going to talk about snap test later, because he is correct. On a snap test, my KV goes way up on that snap moment. Why? Wide open throttle, least amount of resistance of air. It inhales, it sucks in all that volume. So, and now we come into compression with all that air without a restriction. We have a high compression, KV is up. Right? You'll see it on a snap test. But I was talking about here for a moment to see why would I go to a higher RPM versus a low RPM. And that's the reason, because you see, it tells me two things. There wasn't compression. If there was no compression, I would have had a low KV, and whether it was here or there didn't make any difference. Now I know it was a compression. Right? The KV is not because of a spark plug, the low KV. Right? It was there of a compression. So you see, there are relationships that we need to know. Does that make sense? All right, now here's another thing that you may want to talk about, look at, and it is this. The valve spring controls closing, and a weak spring is consistent, always on the same cylinders. Intermittencies may be caused by valve stem carbon. Very common. Very common. Have you ever looked at the scope pattern, and you look at the KV, and it's dancing all over the place? And you give it an oil change, and boy, it is nice and smooth. The engine runs better. Did you ever notice that the engine doesn't run as rough after you do an oil change? You did a lot of oil changes, didn't you? Did you ever notice that?
At $19, it's just got to get out.
Okay, it's a learning experience, I'll tell you. Okay, now let's suppose I see there that KV is all over the place. The engine kind of shakes. And I'm looking at the vacuum, and it is sitting there at maybe a 13 or 14 inch of vacuum. And I take my motor vac machine, I talk to the customer in $125 of, now it's not $19 anymore, okay? $125 job, right? I put an $8 can of soap in there, right? I go through it while I'm doing something else, where I have lunch, and the machine does all the work, and I charge $125. And now I see that the vacuum is no longer 30, it's 16. The same throttle position gives me more RPM, doesn't it? Because I was losing my compression. The seating was not always there. That's what that up and down motion is. I'm not talking about the DIS. DIS is garbage. Okay, we'll look at that later. Okay, we have a reason and another thing to do with DIS. But you see, DIS, we have that fluctuation, and that's why it is very hard to use a scope pattern on DIS. But when we see that on a normal scope pattern, we see that changing of KV. There's only one thing that can do that, and change the compression. Now let's suppose now I see my KV here, and it's doing this, like so, like clockwork.
You're in closed loop.
I'm what? On one cylinder.
Closed loop. If it's like clockwork, and a KV just going a little, it's moving the air fuel ratio, maybe? Rich lean,
No,
maybe?
no,
Like
that
clockwork, no.
No, it is clockwork. Okay, I sold a scope analyzer because of that. It was at an international harvester dealer, and I've been trying to sell them a scope for a long time, and they called me one day, and they have a problem here with this car, and I looked at that, and I see that 1 kV going doing this and that. And because I knew that valves rotate when they seat, and sometimes it was seating, and sometimes it was not seating, sometimes it was a beautiful clockwork, right? I said, you got a valve seating problem, out around. And they fixed it, and it cured it, and I sold the scope. It was thinking on my feet, because I saw that clockwork, and I said, bam, what is that? And knowing that the valve rotates, okay, that made the sale. If I wouldn't have not known, I would have never thought of it. So it's important that you know how it works. All right? All right. We want to go back here, and in order to go back, we look for a blue arrow, right? Return. We have A and D not answered yet. So let's just go back there for a minute. Here we go, A and D. Scope. KV demand may well be drastically reduced by any loss of compression. However, there's a noticeable difference in the firing time depending on the cause. Why is that? All right, let's just step through it for a minute. A typical worn piston rings, note there is no turbulence. Worn piston ring, the pump is just tired. It doesn't inhale very well, it doesn't compress very well, right? But it doesn't inhale very well either. So it is really tired. Okay? This valve seating, valve not closing, there is a turbulence created by escaping gases passing the spark plug. Nah, you gotta be kidding. Am I kidding? Okay, do you see that turbulence there? A hash? We verified it with a cylinder balance test. We already discussed that, right? At low speed, a burned valve or so will show up at an idle and not at high speed. Right? So that verifies to me that yes, it is a valve. And that turbulence tells me something. And the turbulence was on IATN one of the big issues when I saw that. Okay, and I said, okay, and the cure, they gave the cure, and then somebody said, yeah, I've seen it on you know, Bosch injectors and so on and so forth. And of course, I was in a controversy there, and I said, no, that's not what it is. It's valve seating. All right. So let's look at that for a minute. Now, let's prove, and let's look at what the turbulence actually, how it is created. What causes turbulence? It is actually escaping gases passing the flame front. Now, are you not from Missouri that you prove it? You see, is that true or is that not true? Can you imagine that that could be true? Okay, shall we prove it, that it is true? Okay, prove it. For the curious, it's this. Electricity takes the shortest route, spark plug, MF vice, right? Have a spark flying there. Unless persuaded to make a detour. And now I take a straw and I blow at that spark. See what happened to the spark? That's the turbulence created. You think that happens inside of the combustion chamber? You think I'm joking? It could be. Do you believe it? Yeah, you believe it. All right. So basically, here's my airflow, but don't rely on someone's experience. Try it for yourself, capture this on a scope pattern, and then teach the next generation. I want you to do it. And I want you to look at a scope pattern. Don't believe what I said. Okay? You have to do it for yourself. On your scope, not my scope. Your scope. When I say work with a vacuum gauge, your vacuum gauge is way different than my vacuum gauge. I can give you all kinds of reasons. Okay, now then, let's just look at it a step further. See the blue arrow there? We're going to click on that. For the skeptic, do you look at that spark plug? See what happened. There's clear evidence that the path of pressure escape was in this direction. You believe it now? Look at this. There's a close-up of that particular spark plug. I went closer with my lens and look at that. The electrode is burned out on one side. Note the rounded center electrode erosion and the heat discoloration of the porcelain on this side of the plug. What do you think what was wrong with the car?
Plug was it upside down?
Pardon me?
Burn valve?
Yes, absolutely. Absolutely. Mind you, it was not for a week or so. You know, that spark plug wasn't there for quite some time. And that's been put for a long time. So, but here's a typical example of that is what happened. And that is what we see inside of it. So, now we have some proof.
Spark plugs out of perfectly healthy engines that can look like that.
Yeah, right.
Right?
Yeah, right. Yeah. Okay. There is a lot you can see on the spark plug, and there's a whole story about that. Okay, but you know, in order to say, well, I don't believe that hash there, that has anything to do with it. Yes, it does. And here's some kind of a proof that yes, there is a difference there because the spark is definitely detoured. Does it make sense? Okay, go back to my blue arrow to go back where I was. I don't want to waste too much of you guys' time. Okay, So what have we done now? We have actually gone through all that system and we said, okay, what about visual inspection, sound, noise, and so on and so forth, power performance. Power performance, we see now that power performance and scope are the predominant. See, on all the things that we have there for how we can prove it out, power performance and scope pattern as predominant. So scope is a tremendous tool for us to do the diagnosis. But we need to know what it is like. And as I said before, I'm going to convince you today that you're not going to memorize, that you're going to analyze. All right? I want you to do that. And I'm going to force you to do that. If I had more power to do that. Maybe I'm getting old for that. Ignition failures. Okay. What is the objective? What is the ultimate goal of ignition at any speed, any load, any fuel, common to any make or model? Now we've got to be a little bit broad-minded here. What is the objective of a race car driver to win the race? What is the objective of getting the most out of that engine?
A peak pressure occur at the right time.
Right, the spark occurring at the right time. What is it?
Well, it's probably, what, 14, 15 degrees after top dead center?
Very close, between 10 and 15. Between 10 and 15, some 11, some 14, some 15, you know. So anyhow, it's got to be after top dead center, right? Now then, if that is the case, how do we achieve that? Right, and of course, the answer is peak combustion at 5 to 10 degrees after top. You must be an old-timer who worked on a lot of engines. You got some good answers. Okay. What is required to achieve that? Of course, timing advance, initial timing and total timing. Spark duration for as long as there's fuel present in the combustion chamber. How long is that spark? Remember that HEI came out and therefore we had a longer firing time. Before that it was about 1 millisecond, right? And now HEI came out, it was about 2 milliseconds. Now who needs all that? Well, at that time they needed because the spark plug gap was 85,000. Remember that? 85,000. Boy, what a disaster. Because you see, the insulation was not built for that. Making that spark plug gap that big, you think that the spark is always going to go there under compression too? Come on now. So we replaced rotors and distributor caps and wires and you name it. It was a heyday. Then they went down to 65,000. That was a little bit better, not as bad. But then, of course, they went to 45,000. Now, why did they go to 85,000? With that high energy ignition, they had a duration. Huh?
They had a carburetor on the top of that mess.
Oh yeah, but hey, fuel is fuel. Okay, they had to make the mix extremely lean. And make it extremely lean takes a lot of kV to fire, right? And therefore it reduced the firing time. Now they had so much energy, hey, let's overdo it, because if I have a 4-lane highway and I want to shoot a bullet, I have a better chance to hitting a car than if it is a 1-lane, right? The wider the gap. So to hit all those molecules of fuel, make it a wide spark plug gap. Well, it backfired. Of course, but you see, but that was the whole idea behind it. Therefore, we got stuck with that long firing time, and boy, did that help in burning the fuel. If you ever know that the longer the firing time is, we also know that we have more current flow, right? Because there's a more energy in that coil to initiate it. And the heat is what makes the fuel burn. And if you don't believe it, go to a magneto shop. Have you looked at those sparks? If 8 cylinders are firing and a spark that big, it's deafening. You can't even talk to each other. That's how noisy that is, right? That's the spark which they use in race cars. So we don't go that overboard, but at least, you know, you need the firing time. Because the longer the firing time, the more current that you have. And current is what makes heat, right? Anybody who did some electric welding knows that. If I crank the amps up, right, my rod just welds right down there. And it melts, right? I melt more metal with more current. So that is directly related. So then, the spark temperature is important for adequate combustion, and how do we verify that? Firing time. Always firing time. And if I don't look at that, then of course I'm not doing a job in my diagnosis. Okay, let's look at a restricted exhaust. Can we give us some reasons for a restricted exhaust? Let's say a single cylinder. Single cylinder. What can be causing that I have a restricted exhaust? Worn cam lobe, yes, collapsed lifter, basically the same carbon buildup. Same thing what we had in, and of course if it is all cylinders or even one bank restricted catalytic converter. Okay, what we need to know is what's the most effective RPM to pinpoint which cylinder, bank or total exhaust system. What is it?
Should be higher.
Right. Resistance has the greatest effect when there's maximum flow. Think about the fuel filter. Think about a restricted exhaust. Restricted exhaust at idle wouldn't make any difference, right? But boy, when I climb that hill or pull a boat, does it make a difference? Okay then. How can we check for restricted exhaust? Describe a test procedure. Ignition scope. Let me skip the scope for a minute. Let's go to the vacuum gauge. Can you use a vacuum gauge for restricted exhaust testing? Sure. Okay, how? Give me one example.
Hook the vacuum gauge to the engine, go to high RPM.
Okay.
If the exhaust can't get out, vacuum, you have no vacuum because you can't get it in.
Okay, so, give me some numbers. Let's suppose that you're at idle, you're sitting at 16 inches. Right, now you go to higher RPM and then what?
2,500 RPMs maybe.
Yeah, and then what?
Well, as the pressure builds up in the exhaust, you're not going to get any air going.
Okay,
into the
what
engine.
numbers are we looking at?
Oh, 5, 4.
5, 4. Okay.
3.
Okay,
Go right
so
close to 0.
there's the proof. More flow, greater restriction. There's your proof. Right. However, anybody else would use a vacuum gauge different than just at this in high speed?
Well, you can bring it up, hold it there, crack it wide open, and let it go.
And what do you
Well,
read?
what we hope to see,
What do you
as
hope?
soon as you let it go, you hope to see the vacuum rise. If, on the other hand, when you let it go, if the vacuum stays down near atmospheric pressure, that would indicate that the gases are not getting out. Maybe they push back into the intake manifold.
Okay. All right.
And that would be a case where you want to...
This guy is sharp, isn't he? He's an old time. He's worked with that. He does it with snap tests. Now I'm going to do my interpretation. Okay. When I have no business to take a vacuum gauge and verify a restricted exhaust unless I have seen at least 10 cars with my vacuum gauge doing what it's supposed to do. If I don't know what it's supposed to do, I don't know what it is doing or not doing. So what you have to do in the next week, you have to go to the car next time, hook up a vacuum gauge, a good car, and do that and see what your vacuum gauge reach. And not one with a vacuum hose all the way through a boom into a big box. No, a vacuum gauge with that short hose. That gives a change, okay? With a biggest hole, possibly, and central to all cylinders. Not just on one end and see a little tiny hole. And what I would do is I would snap the throttle. And what I would see on a good engine is 4 inches, 24 inches, and come back to 16, or 15, or 14, or whatever that is. Right? 4, 24, and back again. Do it. Do it on a good car with your vacuum gauge, and it becomes a wonderful tool if you want to verify anything. Don't drop the exhaust, don't drill holes in the pipe, don't take the oxygen sensor out, do it with a vacuum gauge. I got a better method, but let's look at that. But that is how it proves the point here, that resistance has the greatest effect with a maximum flow. Okay? Now then, how would we do it with an ignition scope? Let's go to that. Have you ever looked at an ignition scope? And where am I here with my? Oh, there we go. There, scope. What is pure logic telling us? I'm going to walk you right through that, and it's maybe an eye-opener. If the evidence clearly indicates this is not a lean mixture, Look at the arrows. This is not a lean mixture at the beginning. See that? No matter how bad it is, it all starts out, it was not a high kV. It was not a lean mixture to start with, right? But when it was now under compression, or when there was a back pressure, what happened to my hydrocarbon? It goes haywire. All right? So therefore, then the scope shows reduced hydrocarbon. We must also conclude there is also a reduced oxygen. Right? It's not a high kV. Also reduced oxygen on all cylinders. Now, the evidence of course comes up is it's a restricted exhaust. Now, how do we prove it? It's worse at a high speed than low speed. At idle, it may be a nice scope pattern. At high speed, it's bad. Okay, same thing. Higher load, higher speed, it's worse. I do a cylinder balance at low speed, beautiful. All cylinders are perfect. I go to high speed, barely. Doesn't make any difference whether you kill a cylinder or not. That doesn't do anything to start with, right? And of course the customer's complaint will substantiate that. Does that make sense? There is a typical example of that the hydrocarbon there is scattered all over the place. Now let's just look at that. When that goes up, that's higher resistance. Then it sees the molecule of fuel. Then it doesn't. Then it sees. That is exhaust. That is molecule of fuel. That is really a lot of exhaust. Oops, it found a molecule of fuel. That's what it sees. Right? Conductivity and non-conductivity. I see some puzzle faces here. I'll get back to you later on, and I'll prove it.
Just an EGR valve stuck open?
Yeah, absolutely. On all cylinders. Likely affecting more than the other. If you say, hey, if the EGR valve was located here, yeah, I would say that. But you see, if the EGR valve was stuck open, yeah, that could be, because now you're inhaling more exhaust gases.
Yeah, but EGR would affect idle more than it would affect.
Right, it would be. Right.
You have
Right.
good idle, you have bad under load, it's not EGR.
It would stall. Right. But, you know, it could be. But you do that it's stuck open. Quite often when you find that a stuck EGR valve, the customer comes off the freeway, right? He takes his foot off the accelerator and the engine stalls.
I realize all that, I was just referencing.
Yeah, hey, absolutely. Absolutely. It's a matter of fact, if you have one condition where there's only one cylinder, I would think that then you're going to look at your data, say, where's the EGR? Oh, there it's located, right to that next cylinder. It's a matter of fact, when you do a cylinder balance test, right, then, and you do it off idle, then the EGR normally opens. And normally the EGR valve inhales about 7% of the exhaust gases. That's normal, right? What will happen with a restricted exhaust? It inhales a whole bunch, right? About 35%. So therefore, with an EGR valve open, or even when it opens with a restricted exhaust, that is what actually happens, right? Because at high speed, we do have an open. All right, now. Now, what we wanted to know is this. When we do a cylinder balance test, and we do not disconnect or inhibit the EGR valve from opening for a cylinder balance test, what can happen? When you do a cylinder balance test, you want to inhibit the EGR valve. I'm killing a cylinder. Let's put it this way. All cylinders are lean to start with.
The pressure pulses in the exhaust are going to vary, and that's going to change the way the EGR flows into the intake? No?
Okay, let me explain it. Maybe that gives you an answer to you. What basically happened is that all cylinders are kind of starving. Agreed with that? When we, back to carburation time. We set the carburetor to the highest RPM, lean roll. What does the oxygen sensor do? Lean roll, right? When I add fuel, I can always increase RPM. Any car nowadays, right? Okay, so we are always on the lean roll. You kill a cylinder, and the EGR valve is now open, let's say, and the raw fuel is in the exhaust, inhaled by the EGR valve. That makes all the other 7 cylinders come alive. and I don't have any difference in my reading. I say, I found a bad hole. That was a bad cylinder. Okay, especially the one that's the closest to the EGR valve. But that's a possibility, right? Do you see the reason why? It only has to, all what it needs is maybe some microseconds of more fuel for the engine to pick up RPM. And if all of them pick up a little bit of RPM, it cancels out whatever I killed. One dies, the other 7 come alive. All right. How did I get to that discussion? All right, let's go back to our discussion here about the mechanical condition. Am I boring you, or are we doing okay? Okay. We have gone the restricted exhaust. If I have a lab scope, I will do something different, but I'll leave that for later, because I come back to a lab scope testing later. Then we'll look at that, okay? How to check the exhaust with a lab scope. Power performance per cylinder, yeah, of course we know. At high speed, you know, it's a lower performer than at low speed. Okay, let's go to the next. The voltage required to fire the plug. Let's look at the scope pattern for a minute. The voltage required to fire the plug is determined by the greatest gap in the circuit. Remember that on IATN 7-8 years ago? That is how I got the name of ignition guru, because I said resistance has no effect. The kV demand is determined by the greatest gap. Not rotor air gap, plus spark plug gap, right, or whatever. It's the greatest gap. Therefore, when I see a waste compression, waste is high, compression is that. If they happen at the same time, I'll only see this one. If I separate it, I see them here. Now, can you imagine on DIS? Here's a waste, there's a compression of the same cylinder. When this is higher and this is the same, what is my problem? Higher than all the others, if I look at all the waste.
Poor compression in that cylinder.
Pardon me?
Poor compression in that cylinder.
More compression?
Poor.
Or poor compression?
Less compression.
Less compression on this cylinder. Because it is higher, that would be more compression. And this is waste, so therefore waste has no compression anyway. Right? This is the same. The compression stroke is the same, but the waste is different.
The waste is different, not enough.
That's a bad wire. Why do I know? Because the wire was bad, it was required 8 kV. This guy said get 12 kV. I won't see it. But when I'm in waste, I will see it. See? That's external. Now let's suppose that this is high compared to the others, and this one is also high compared to all the others. My compression and waste both are higher. What is wrong now? Plug gap. Because the same plug gap I have in the waste is a compression. And in compression it affects, it increases, and compression it increases, right? Does that make sense? Think about it. It does, anyway. I'm not going to stick along with this. Let's look at that. The voltage required to fire the plug is determined by what? By a gap. There's got to be a gap. Any gap. Without a gap, I will not see kV. I have no ionization unless I have a gap. Whether it's a spark plug gap or a break in the plug wire, whatever it is, there's got to be a gap. And if I have a foul plug in a system where I have a distributor, I still have rotor air gap. When I have a foul plug on a DIS, I have 0. Right? That's why I always see a low kV when I have a distributor, because that's my rotor air gap. That's how you can tell whether what your rotor air gap is. Now then, now we add here compression, and what happened is the kV is going up. kV starts to go up. Then when I add here hydrocarbon, the voltage required to fire the plug is lower. So there's a combination here, what's happened inside the combustion chamber. So that's why kV is telling us a lot of stories. Now let's start all over. Here's my gap. Here's my pressure, right? And here's my hydrocarbon. That brings the compression down. Now, one is constant, the other one is variable. The variable is whenever I change RPM. So if I change the RPM and that kV goes up and down, I know that my greatest gap was in the combustion chamber. It was not external. It was affected by pressure and it was affected by fuel, or maybe both, or maybe one of them. Does it make sense? That gotta sink in, that gotta make sense. Because based on that is all a diagnosis of whatever we do when we're looking at kV demand. All right then, when hydrocarbon is taken out of the equation, what will happen? Very important to know. The voltage required to fire the plug is going to go up and up and up, and it becomes higher without fuel. So if I ever want to check a compression with kV, I do that while cranking the engine, and I step on the accelerator all the way to the floor, no fuel. And if I have a kV of 18 kV or more, I have compression, I have a good coil output, I have no foul plug, I have no crossfire. I know that that engine is good. 15 seconds cranking. And I have all those answers if I could look at that. Do you see what I'm saying here? If I don't have, if it is less than 18 kV, or one of them is less than 18 kV, it could be low compression. It could be low coil output, if that was one coil, or a separate coil, right, than the other plugs. If I have one coil, of course it cannot be, right? But it also could be a crossfire, that crossfire is 16 kV. I would never know when I'm driving at 14 kV. You know what the biggest thing would happen when I pull a plug wire, you know, to see if the power performance is there? Yeah, it's good power. Let me do the other cylinder. Yeah, good power. And I have an HCI system, a distributed ignition system with 40,000, 50,000 volts kV capability. You think the car spark is going to say that, oops, I'm not going to go anywhere. I'll tell you, it's going to go someplace. You may not know that, but it did. Okay? With that capability, by pulling a plug wire. And people do that every day. And you know what happened? What happened is that now the spark occurs, let's say, at something like 18 kV. As long as I drive at 14 kV or 15 kV or 16 kV, happy-go-lucky, I'll never know the difference because that was the easiest path to go. But now I'm on the freeway, I'm 60 miles an hour, I want to pass somebody, bang, there comes the car from the other side and I'm in an accident. Because the dumb shit took the spark plug off and it just created their fall. It's bad. How come then, if we have a bad plug wire, that it doesn't do the same thing? Because a bad plug wire is not an open circuit. A bad plug wire burns away carbon a little bit more, and the engine misfires because the firing time becomes so short. But it is not 45 kV. No, it is now maybe 22, 23, maybe 26, maybe 30, but not enough to crossfire inside of that coil. Now, unless I keep driving with that bad plug wire, it becomes brittle, and now it becomes a bigger gap and a bigger gap. But that's not the same as pulling a spark plug off in order to test for power performance. So think about it. All right. The absence of fuel will also affect the firing time, but we are leaving that for later discussion. We are looking at kV now. Okay, the objective is to evaluate kV supply and demand, locate abnormal behavior, determine cause and effect, and verify with a scope. All right, so what do we know? The voltage required to fire the plug reveals a lot about spark plug gap, open plug wire, rotor air gap, lean mixture, timing advance, but also mechanical condition like compression and various valve malfunction. It's an awful lot of things that you can see in the kV alone, right? If we do and use it. Now there are different ways of looking at kV. I don't have to have a scope. I'll give you two ways of doing it. We're going to have different ways of diagnosing beyond the scan tool. All right? And there has been a lot of problems with some people not understanding the scope, especially when it comes to DIS. Why is it? Because the kV is all over the place. So I'm going to give you here another option. I'm going to cut this one out and let's do some playing. Here's an engine. Okay, let's say that's one cylinder. I'm going to work here with one cylinder. Let's insert a T in the kV source and connect a neon light. Why a neon light? Because for neon light it takes 90 or 70 volts to fire. Well beyond my battery voltage. Okay? So in other words, there has to be a collapse of the field. Remember that. We add a spark gap adjustable from 0 to 22 kV. A normal setting is 18 kV. Then we connect it parallel to the spark in the combustion chamber. Now there's the interesting thing. I connected in parallel to the spark in the combustion chamber. And therefore I can put a T here. Like say that is a T. Right? And I can put it there. And I can therefore, one goes to my coil tower and the other one goes to my spark plug wire. Right? And now I'm in, this is my complete circuit right here. Right? My completed circuit. And there's my T. If this is in parallel, you can readily see now that if this arcs over, if I just turn it until this just starts to arc, that the voltage requirement here is almost identical to what's in the combustion chamber. What happened in the combustion chamber? If I turn it in and it always sparks here, it's not sparking there. If I turn it open a little bit further, now it's sparking in the combustion chamber. Parallel. Not series. Okay? There is an awful lot of information there. Can you imagine that? Now let's suppose that every car had one cylinder. Then it is easy, of course. If it has 8 cylinders, I've got to do it 8 times, whatever I'm doing. Now you can imagine now what happened. If I go all the way down to the bottom, I have a cylinder balance test for DIS ignition. Right? Cylinder kill, low speed, any speed, whatever. I also know that if I have lit and I crank it over and have a dead engine, that if that lights up, that my crank sensor works and my module works, because I got 70 volts in the secondary. I can have 89% of my secondary shorting windings and still get 70 volts. I can have a bad coil, but I do know that the field was collapsing because I created 70 volts in the combustion chamber. That's why I have a neon light. There are other reasons for that, but one of the reasons, and it's a buffer, it also gives me an indicator, a light, so I can crank it and I can see that, yes, I do have that condition. Now, can you imagine what would happen if I have a condition where I just make it misfire? Okay, there I turn it up, misfire here, that means now it is firing inside the combustion chamber. Now I step on accelerator and the load, and what happened? All of a sudden starts to fire here. That proves a point. That proves to me that it takes more kV to fire now under compression or under load than it was at idle. Right? So it gives me a lot of information. It also gives me information at idle when I turn it over and it misfires here. I rev it up, what happened? It stops misfiring because now it fires here. Why is that? It fires in a combustion chamber when I rev it up. When I come back to idle, it fires here.
You change the timing, Bob.
Timing, yes, I know that my timing works. I also know that I had compression because of course, you know, it's under low compression. All I did that with a spark gap, I can make one like those, right? You could make it. Little tube, neon tube. You cannot buy that neon tube, you special order them. Because you can neon tubes, neon lights, but they're not bright enough to give you any information, that they're fairly unstable. So we come up and we just did some of that, okay? Here's the reason, guys. The reason why we did that is because when they first came out with DIS ignition systems, right? Everybody had those big boxes. And DIS has positive, negative, it has waste and compression, and those boxes, they don't work only on one, only negative. Then you couldn't reach the spike going down. So consequently, here we made a box that you could do that, and you could also kill cylinders with just activating some solenoids and shorting them out. I sold a lot of those because now those old boxes, those big scopes, were all of a sudden worth something again because you could do DIS. All right? Then 10 years later, I go back in the field, and the guys are still using it, in spite of the fact they don't have the old box anymore. They have now modern equipment. They bought a Vitronics or something, or whatever it was, that was able to do waste and compression and all of that. And they were still using it, because we're still in the balance testing. Then I said, well, you know, if that is a valuable tool, I'll make a bunch of them, and I just put them all together, and I put them in a box, and sure. And now the high schools buy them, you know, colleges buy them, because that's so easy to instruct, to show what KV does. Because you can see it, and you can observe it, and you can recognize it. Now you have something that can work on DIS. All right. So I'm going to give you this as a hint that yes, you can make a spark gap. You can make it yourself. You can buy some tees or make some tees. We have it available if you wish, but neon is an ideal indicator of a point of ionization. It is a current limiter and a buffer. In other words, I never have an open circuit. If I start the car up and I have an open circuit of 22 kV, right, and I have them all firing up and they're all open, I start the car up and it lights up, now I know I have an open wire. I know which one it is and fix that first. You cannot do any further diagnosis unless you fix that bad wire, right? Because that affects everything. Why does it affect everything? I can do still a balance test. I don't know whether it still have any power unless I fix that wire, but not only that. It screws up my mixture terribly. The computer goes haywire, right? And the balance is off, and it sets codes, and you name it. All right then. So we can demonstrate a crossfire. I'm going to go quickly through this. What do you think is happening here? Start the engine. If the neon light lights up very bright, we have a problem. What is the problem? What is the problem? An open plug wire. Yes. Why is that? And here's an interesting thing. We know that there's a bad plug wire, right? So we have an open circuit because it's a lot easier to fire in a neon light than there is inside a combustion chamber. But here's, what else do we know? If I see that, I said, okay, I have an open plug wire, I have to replace it. What else, what more information did I get?
The primary was good.
Okay, yes. Yes.
That's all I had on that.
Well, the coil output was good too.
Yeah.
22 kV, that's a good coil output. I just did a coil output test. 22 kV, that's a good coil. You know what it also tells me now? That I don't have to replace the module or the coil, whatever. Because the bad plug wire didn't do any damage. If I have still capable of 22 kV, right, I'll never need 22 kV. Unless I wear out the spark plug until it is white cross firing across, there's no electrodes left. Goes from the inside of the porcelain to the outside of the shell, you know. That might be 22 kV. So you see, there is so much information that is there by telling me that, yes, it is fine there. That tells me that it is way greater than this. So consequently, now I know that I don't have to replace all that. Most people, when they replace a wire, they say, oh, I don't want to take a risk, Mr. Customer. I'll replace the module and whatever, and the wires and whatever's in that circuit, maybe the coil too, and if it is all the whole coil pack. Because I don't want to take the risk when that was on an open circuit that you still have a good circuit. But remember that plug wire did not do much harm until you pull it off. The worst thing that you can do, and here's the thing, I see people take the coil tower from one coil tower to the other. That's a good coil output. That's bull. That will not tell you that there's not crossfire in the coil. It's not connected to ground. It has no reference to ground. It's coil to coil, right? If that's crossfire to ground, doesn't matter. That is just one side of the coil, basically. From coil to, yeah, sure, coil will do that. And it can be leaking from one end to the other. The only way to know it is if you do it against ground. Now you have a potential, say, is it there or is it not there? Does that make sense? All right? So then, Let's suppose we use a spark tester with neon light and set the gap at 18 kV. Then we crank the engine while the fuel is inhibited. If the neon light lights up, what does it tell us? The neon light lights up. What does it tell us? A hint. The external gap in that neon light, or below that neon light, out there, right? The external gap is 10 times greater than the internal spark gap. 10 times greater. And yet it shows a fire there.
You got compression.
Right, under compression. 45,000 gap is the equivalent as a half-inch outside in parallel. Half-inch, that is 50,000, right? Did I calculate that right? Yeah.
You said don't write, right?
You want to remember that? No, you've got to reason it out. Don't memorize. Reason. Okay? Does that make a difference? You see now how much more demand there is inside of that combustion chamber, and if the demand is high, it tells me so much information that yes, there is a spark there, and it is maintained for that length of time, and therefore it is the capability that it has there. Good coil output, good compression, no crossfire, no foul plug, all of that is there if I crank the engine over and do that test. And if I do that on all cylinders at the same time, I have a bar that we just lay up here, right? And you lift this up and put them under there, and you flip it down on the bar, and that's 18 kV. So by doing that, I do all my testing. And I can do a total diagnosis with DIS in less than 5 minutes. All right? So test results, compression test is okay. Coil output is okay, and there's no crossfire up to 18 kV. Test completed. Now then, what about if it does not light up? What does it tell us? Low compression, fouled or shorted plug, crossfire, low or no coil output, any of those possibilities. That's not enough information. I need to know why. What is my next step? What would I do? It's not lighting up. So in other words, if it is not lighting up there and it's 18 kV, then there is something that takes lesser kV demand here is lower than 18 kV. That's what it tells me.
Pull the wire up. Man.
Hey, you got it. And what does it prove to you?
Well, no, I was going to tell you all the stuff you knew before. You know why.
No, all what you know now is the coil output is good. 1 out of the 4 I know is good. Okay?
I'm sorry, I didn't play it fine. Well, if it wasn't lighting before,
Okay.
and you make the open now it lights, you know that the coil is good, and you know that the primary was good, all the rest of that.
Okay, that's the coil. The coil output is good. But I don't know if it is a foul plug, or I don't know if it is a crossfire, or compression, or anything like that. But I do know the coil is good. So 3 more to go. What is my next step? How can I prove if I have a crossfire? Turn my gap in. If that starts now, let's say at 16 kV, that's where the crossfire was. If I go all the way down to the bottom, and now I get a spark at my knee, that was a foul plug, right? You see how that has a relationship there? How with the kV, whether you do it with a scope or with a spark tester, kV is giving you an awful lot of information. Does that make sense? Now it has to sink in a little bit. Now you have that same disc, okay, what I'm doing here now, and go over it and find some flaws in it if you can, okay? Likely you will, okay, and hopefully you will, so I can learn too. But I've worked with this, and I've taught this class to high school students who had a hard time learning, and guys who could never understand the scope because they were memorizing it, and it is analyzing what you have to do, and once they learn how to do it now it becomes easy because half of the problem is already gone. Okay. Okay, we're going to have, let's have an intermission for a minute, for a few minutes, okay? What's the next logical step? I'm going to ask you this. kV demand here is lower than that. And the possibilities are disconnect the plug wire. We already did that. Okay. let's do something here. We're going to work here with a hard or no start condition. All right? And let's suppose now that I do have something like a spark gap that I work with. I'm going to walk all the way through a hard or no start condition, and within 5 minutes I will know exactly what the problem is. And I want you can do that with a scope too. Okay, there's no need that you need to, as long as you can read KV for some reason or another, okay, you can do it, except you cannot kill cylinders on DIS without getting into the secondary and killing it, really. All right, I'm going to the first step would be the ignition test. I would disconnect everything on the coil and go directly to the firebox, right? So now I'm going directly here to my spark gaps. Wide open, 22 kV, crank the engine over, and I know whether I do have a coil output. Okay, bingo, my whole test is done for coil output, every cylinder. All right, now I have to do it 2 times. First of all, I have to kill one side of the coil, okay, one side of the coil, and open up this and read this. Then I crank it over and I look at this one and do it that way, 2 times. Now why 2 times? Because I want to see each side of the coil separate. I don't want to go from tower to tower. I want to go each side separate because I want to see if that coil is indeed doing the job when it comes to a ground relationship. All right. So by doing it 2 times, I do also something else. I crank the engine twice. Now it stabilizes my cranking speed, and that is important for me to see whether my crank sensor is indeed stable. All right. So if I have a coil output, the purpose is the objective is to determine if the coil output is capable of jumping 22 kV. And if fail, we identify which coil, which module, what cylinder, or whether it is the ignition system from crank sensor to coil output within 3 minutes. That's the objective. All right, so let's do that. So no T hooked up. And let's say that the coil output is okay. So now, if troubleshooting is just as important to know what it's not, and since fuel takes fuel compression and ignition to make the engine run, ignition checks out okay, that leaves only the lack of fuel and compression. Agreed? Those 2 left over. Okay, let's look at compression. So we have the rule 1 out. What is the next step? Compression, 2 observations. If we want to consider lack of compression as a possible cause of no start, it has to be more than 1 cylinder. Agreed? Almost all of them. Okay. And the most logical reason would be a valve timing. Now if that is valve timing, I would know right away from cranking speed. Right? I mean, there's no question. If there's a broken valve, broken belt, then, you know, hey, there's no compression. But this, hey, there is compression. All right? So therefore, if I do know that, then my next step is fuel. Now what would you do next if it is fuel? Since ignition system checks out okay, compression is unlikely based on the cranking, then the fuel pressure needs to be checked, but also fuel volume. And while I'm at it, look also on contamination. Look in the bottle and look at it, because somebody might have put diesel fuel in there, who knows, right? Or a combination of. By the way, did you know that if somebody has used 85 and goes back to normal, that computer goes haywire? Because it's setting itself for 85. You have to disconnect the battery in order to have the computer relearn. I found it out. Hey, this car was running bad, unbelievable. So finally somebody said, hey, you know, did you use 85? Yeah! Ah, the computer learned something new. Now it has to unlearn that. Yes, it has to start all over again. I didn't know that. I don't know much about 85, but I do know that it has some of the questions. All right. What if all systems check out okay, from ignition to compression and fuel, and the scan data has no given any direction about the no start condition? Now I'm up to quick. Now I have to really think. Right? What's my next step? Next step will be time consulting vehicle specific data. Using schematics, service bulletins, IATN, a good friend you have in the business. Look for common to all cylinder trouble spots like power input and ground, but above all, 5-volt reference voltage. If I have one sensor that's shorting, that kills the 5 volts, the whole system is dead. Everything dies. Don't forget that 5 volt, measure that. If there's a sensor that is shorting, you don't have 5 volts. Maybe you have somewhat, 1 or 2 volts, you know, because there's maybe something there, but there's a load on it somewhere. And that is a good, no. Yes, now you have done everything else, but the most important thing is you have eliminated here 95 of all the possibilities of a no start, right? And yes, now it is going to take you more than 3 minutes or 5 minutes. All right then. Now let's suppose now that that there is a problem when we first start. We do a trigger test. A trigger test means that we actually short out all the, that's not a short out really. Remember, it is 70 volts. That means now that the coil is indeed collapsing. I do know that therefore the primary is okay. And if all of them are fire, right, that means now that the crank sensor works. How does it otherwise trigger? Now if 2 of them don't fire, it's the same coil, that's a different condition than 1 of them not firing, right? Or 1 or 2 not firing of 2 different coils, that's another condition. So let's walk through those conditions. There's usually not more than 3 steps and I have the answer, right? All right then, let's just do that. It either passes or it fails. Passing means when they're all down, they all fire. Crank sensor, modules are okay. I did that in the secondary, remember? It's collapsing the secondary. Now if it is fail, what could it be? It's good when the control modules are okay, coil primary is okay, crank sensor fail. Let's suppose these are possibilities. None of them flash. 23, we go to 23. 2 possibilities. Okay, number 1 possibility is that it is that the crank sensor is no good. So I check the crank sensor output, but there's also a possibility that I have no power. But there has to be power to all of them, right? Common to all. So now I have to take a schematic out, find out where to go in order to go for power for all. I have given directions. I know which way to go. I'm not guessing anymore. Okay, I know where to go. It's not that easy maybe, but I have to go in that direction. Now let's suppose that we have an arbitrary intermittent misfiring. In other words, the flashes that I see is not nicely 1, 2, 3, 1, 2, 3, 1, 2, 3. It is that all over the place. Now we have an intermittent condition. All right? So cranking speed can serve very nicely as an ideal wiggle test. Wiggle test means that when I crank the engine, there's a bit of a shaking, right? Quite often, that's where my problem really starts to act up. Now then, what we look, if this is a typical 6-cylinder, we should inspect a consistent sequence, repeat flashing like clockwork, something like this. So in 15 seconds, cranking identifies faulty trigger source, okay, intermittent. No neon flash on one side of the coil. Now that tells me one thing. If it is one side of the coil, that means that the primary is okay, right? It has to be. So therefore it is a dead short, like a shorted coil secondary. But it also has to be dead short that is below 70 volts for that to happen. Seldom happens, but it can happen. A dead coil on one side. Okay. Why a shorted coil? Of course, because we are looking here at 70 volts minimum. Okay, next one is typically if we have 2 neons won't flash, the same coil. Now we are in a different ballpark. Because now it could be that that one module is not working. Right? We do know that the crank sensor works. That leaves the coil primary or the control module as suspect. Next step is, if accessible, one single test identifies both. I go right across the coil. I crank the engine over. I do it with a voltmeter or I do it with a scope. And if there's a pulse, I know that my module works, but the coil is open. I just completed the circuit with my voltmeter or scope, right? Or if I have a coil failure. So I went here to all the possible problems that we could have. The conclusion is that the diagnosis was based on the failed coil output test and passed the ignition coil test, right? So now all you have to do is, since the test was performed completely isolated from plug wires, it's a true output test depending 22 kV. I need to know, I have to have 22 kV in order to know that I have a good coil. Usually you can get up to 36 kV. But you see, 36 kV is not guaranteed really that you have a firing time. Okay, so 22, if you have 22 kV, you can say I have a good output. All right, so what I did here is basically is a hard start and no condition. I went through the whole sequence of what could possibly be wrong. The exercise is demonstrate that it takes one hookup plus 3 minutes to qualify or identify all functions. Does that make sense? Now, can you do it with a scope? Absolutely, you can do it with a scope, right? But you have to be able to look at that. And there's one thing that you cannot do and check for your output, if that you have to kind of short it out in order to get to the lower kV readings. Does that make sense then? All right. Okay. Now, if I want to do a running test and it's just running and I want to just qualify it, yes, I can do a cylinder balance test and I can do it at low speed and high speed. So what is a running test? What would you call a running test? That's a running test. Okay, how many pictures do you think it takes to make that? What is
20.
4. 4 pictures. All right, so back to work. Okay, the verify a routine performance test per cylinder to perform a snap acceleration test to simulate road load conditions. If I have a good running car, I just want to qualify it. Okay, I may or may not want to do a cylinder balance test, but it is so easy to do to go from one cylinder to the next to say, okay, let's see, what is this one? Short. Okay, next one. Short. Next one. Next one. Next one. So in other words, I have a capability of doing a cylinder balance test. But there's another thing that I have. I can do a snap test. When I do a snap test and the neon light flashes on, what does it tell me? I'm in 22 kV demand. And I do a snap test and the light flashes on. What does it tell me?
Spark didn't occur in the cylinder.
Why would it be a high kV demand for something inside of that combustion chamber to bring it up to 22 kV? That gotta be one thing is missing. Fuel. Fuel. So what do you think what was wrong?
We got a carburetor.
I've worked a lot with the carburetors and I love them, really. No two ways about it. But a lean injector. There is no way that you can tell or that you have any way to diagnose a lean injector, because anytime when the injector is lean, it will compensate for itself. The result is that the injector that is lean, therefore, will be compensated for it. It gets more fuel and more fuel until finally there's still enough oxygen there to make them bob up and down in that lean injector, because all the others are so rich there is no oxygen left. And now I have there, let's say, 5 out of the 6 cylinders which are extremely rich because one was lean. What's the consequences? Terrible. Eventually the oxygen sensor says, I can't see anything anymore. Where are you? Right? Because we carbon it up. 5 cylinders contributing to all that carbon because it's not burning all the fuel. So in other words, we have there the capability of, or the problem really, of carboning up the inside of the engine. Eventually it may run, turn the ignition key off, and it still runs. So the consequences are really bad, okay, when you have a lean injector. But yet, there's some way that we have to have and find out. You can do it with a scope. You have a scope, always do a snap test. If you have a scope and you don't do a snap test, you're not doing the full analysis, because it does happen. And all that it takes is a little bit of dirt inside the injector. It's a matter of fact, you know what makes that quite often the case? When somebody does a flushing test or a flushing of the ignition system. All that dirt that was in the rail is nicely washed out. And where do you think it goes? They put a can of that cleaner in there, under pressure, right? It's only one plate to go, is that screen into the injector. And now your problem is doubled, right? You thought you did the customer a favor, but you didn't, unless you have a machine that takes it out and it circulates it and takes it out. Okay? That is what happens quite often. But it can also happen without cleaning it out. And you see, the interesting thing is this. If all injectors were equally lean, no problem. Your fuel trim will tell you, yes, there's a change. It's adding fuel. But if all of them are equal, I do a snap test, none of them will go up there. Why not? It's not a difference. It's the difference that show up. If I have 2 injectors lean, I may have 2 come up. If I have 3 injectors lean, it's already stabilized enough that I will never find that. Okay? There's another way of doing it, and maybe that you've already seen that with this cup with a fuel trim generator, right? We had a fuel trim generator, and we hook it with a cup, and most of you have this cup. You hook that up to the primary, and this goes up to the ground lead. Okay, and what you do now is you hook this side up to 1 injector. And when you hook it up to 1 injector, doesn't matter which one it is, I'm pushing the button and I'm adding fuel. What will the computer do when I add fuel? Lean it out. I keep on adding fuel. Computer leans it out. I keep on adding fuel. Computer leans it out until it finally is so lean it misfires. Which one misfires? The leanest injector. I found it with my scan tool. Which one was the one that misfires? Or I saw it on the KV, or I saw it on the scope. Right? So that's what the fuel trim generator does. Now, what is in here? It's a little device that makes the injector stay on a little bit longer. And therefore we are adding just a trickle more fuel. If we overdo it, it doesn't work. It's got to be just a precise amount. And holding this in, here's an interesting factor. If I keep on holding that in, I have a count, a misfire count. And it goes up to 70. And by 70 it stops counting. I added so much, created so much oxygen that it balances out. Okay, now then, let's suppose I have 2 lean injectors, but one is a little bit richer than the other. Then the total will be 70. One will be 30, the other one maybe 40, but it still will be 70 misfires. You know, on a scan tool you can see the number of misfires. Okay, figure out why that is. A lot of people have tried to figure it out, but it takes too long to explain it. But that's what it happened. Now if you have a different fuel trim generator, it might be doing it different. Now we have the same thing under load, where we can do it actually with this unit, because that is the same as the COP, but now my fuel trim generator is different. It was here someplace, oh yeah. Okay, now I have a fuel trim generator that is also basically for coil unplugged here, and now I just go to that injector. Let's suppose that I have 6 cylinders on my primary, that's for coil unplugged, 6 cylinders. I find out that this cylinder seems to be starving of fuel. How do I know that? The turbines on the right hand side, you know, it's sloping up. Okay, then I say, okay, what's this cylinder? Okay, let me go to the injector of that cylinder and stick it in there. right? Now I add fuel to that cylinder, and if that cures that cylinder, I know it was fuel. Another worn cam lobe or an EGR valve that's close to that cylinder or whatever. That's how you can add some fuel and come up to a conclusion. It doesn't work on a Chrysler. Why doesn't it work on a Chrysler? Well, Chrysler is very finicky. If it sees that you fool around with the injector, then it says, whoops, sets a code. You know, your test is over. So then it will reset itself, mind you, but you're setting a code. Okay, so what am I doing here is I'm going to go through this. We have already talked about cylinder balance tests at low speed and high speed, so I'm going to say this. You have this on your disk. Okay, I'm not going to repeat what's already on the disk. But there's one area that I want you to have a look at. And it is, there's always a relationship. If I say I come up to a restricted exhaust, then at cranking kV it's okay. I won't have any problem, right? At coil output would be okay, right? At low RPM I have no problem. At high RPM I have a problem. And if it affects all cylinders, yes, that is definitely a fail, right? And under load it's a fail, so that all fails under load. So you have a chart here. I want you to reason it out for yourself. Don't take my word for it that you need that chart. You ought to be able to figure it out for yourself. It's just logic. It comes very easy. Based on the fact that yes, there is a difference under load. All right, you also have this, but I want you to look at that later. And what we're talking about here is that we have 3 inputs to a scope and we come with 9 outputs out. I'm going to skip all that because we are not trying to push you in this direction, but you have to go, if you want to do it under load, you have to come up with some longer leads. And there's an easy way to come up with some longer leads. Here's an important step. If you do load testing in the bay, make it safe. Put some in front of the brakes or of the rear wheels or whatever the drive wheels are, you know, and make sure that you're not moving. Don't just try to do it with your foot and then do some testing that way. I've seen some accidents happen, and you know, if you can do it on the road, in the bay you can do it for short periods of time, you know, but not for a long period of time because you might do some damage to the transmission. But by all means, play it safe and put the hoist in front of it. But I'd like you to dare to explore here. We're talking about the when factor. Testing on the load has some different requirements. To record the exact incident when the problem acts up is very important. Not only for diagnosis, but also to compare the condition before and after the repairs are made. Okay? Because we are really looking at something in a different condition. The TPS is a mechanical operated device recording throttle position and is the only sensor not affected by misfire. It's mechanical. It's a foot movement, right? Whereas misfiring or not, you always get the same reading. It is a mechanical movement. And if I use that as a reference, then I have a good idea of which sensor is acting up at what time. So I'm going to look at the rethinking scope analysis. Now, you have, let's say, 40 years of experience, and it's hard to break a habit. You memorize scope patterns or relying on database with waveforms listed by make, model, and year, but let's break that habit. Because the minute that you think about, oh, there was a Chevy, yeah, oh yeah, I had that same problem 3 months ago. Maybe that's the same thing. Let me replace the mass airflow sensor, because that's what had happened the last time. It doesn't work. Okay? So how do you break that habit if you have to think in electronic terms and forget the automotive? If you think make an engine, you're already prejudging and have no longer an open mind. That's important, okay? Forget that you know engines. Now you're going to look the way that the scope looks at it. Okay? Remember, the scope does not know automotive part. All it knows is voltage over time. So let's do that in 1 to 2 steps. Here we have step 1. Do you recognize the scope pattern? I wish you wouldn't, but you likely do. Okay, read what the scope is telling you. The scope does not know automotive parts, right? So it only knows voltage variations in time. So let's go to the voltage variations in time. Observe what the scope sees. Here it is. Number one, beginning voltage was less than 0.5 volts. Then we have a sudden voltage increase to 4.3 volts within 30 milliseconds. Then the next thing what happened is about 4 volt level maintained for 140 milliseconds. Okay, return to starting point, 80 milliseconds. Now that is electronically what happened. That's what the scope is trying to tell you. Now you put your automotive hat back on, and now you're going to interpret it. Okay? But first of all, what do you think? Can you tell when this capture was, this scope pattern was captured? Engine running, key on, or key engine off, or is there any difference?
We're looking at a TPS, Joe, the club.
Absolutely.
I tell you, there's noise on there, I'm gonna think it was run. If there was no noise.
Oh, you're so darn clever. Yes, you are clever. That's right. There's noise on there. All I want you to see here, that noise is not significant. That's ignition noise. It's not a part of the waveform. See? So don't think that, oh man, I see some spikes there. And the spikes are really gonna tell me that that TPS was bad. No, no. Ignition noise is what you get from all sensors, and especially the lower voltage levels. All right? So yes, you are right. It's a TPS, and therefore we're going to look at it now from the technician's point of view. All right. Put your automotive hat back on. Start interpreting what this means in automotive terms. The interpretation of what the tech sees and what he thinks, hopefully. Number one, the TPS at rest at 0.4 volts. That's pretty well within specs. Good information, right? Then what does this tell me? Snap acceleration, good response. Look at the steep line there. Okay. Held at near wide open throttle at 4 volts. That is near wide open throttle. If you're all the way down wide open throttle, maybe the engine dies. Likely will. Okay. Good solid line. There's no interruptions there. No break. All right. Important note. This is the only pattern total driver control that ever is the ideal scope trigger under load. The last one, of course, was release at TPS at idle, so the spring tension was good. How often do you have that the spring tension is not good and it hangs up there? You know, from this one sweep, you know all of that is an A1 condition. Now, since that's on an A1 condition, I'm going to do it for diagnosis. Let's look at the customer's complaint. And there's no power on acceleration. My first reaction is restricted exhaust. Hook it up to a scope. Okay? What do I hook up? The TPS and a mass airflow sensor. Why the mass airflow sensor? The mass airflow is a response of a mechanical movement of quick acceleration. That's what I want to prove. Just the same as we did with the vacuum gauge. Right? We want to see how quick the response was of the flow. Therefore, the objective of this test is to test for an exhaust restriction. Observe the instantaneous response of the mass airflow sensor to the TPS rise in voltage. That's what we're looking for, right? What a beautiful way. And here we're still trying to have that situation of dropping the exhaust. Now then, these are the questions that I get asked at a seminar. The observation is verify back pressure, right? And here are some of the questions. Are we concerned about the waveform? No. Maybe it is right, maybe it is not right, but that was not the intent. The intent was to find out what the response of flow is. I'm not diagnosing here the mass airflow sensor. Now, if I know something about what it should be, yes, I may see that there's a little wave, but that is fairly normal, right, until it comes to rest, right? There is a fluctuation. When I do a snap test, there is that rush, and that's what I see. And a mass airflow sensor sees it too. So yes, there is information. What about the mass airflow sensor which does not use an amplitude but a frequency change? So what's the difference? We're looking for response. That's what we're looking for. You see, we get so hung up with, oh, let me just look at that scope pattern, and you spend time looking at something that is not material, that does not have any reason for you to look at, and therefore you're wasting time. You have an objective, you aim for the objective, you start there. Why go to a database to check what a good defective waveform looks like? No need. I'm looking for response. See that the curve that I had on my foot was the same curve I had there on the mass airflow sensor? It was not, oh yeah, it finally got there when my foot was already here. That's what I'm looking for. And how simple is it? Do we still want to look at an exhaust or drill holes or remove O2 sensor to check back pressure? No. What about the map sensor? Can it do the same thing? Absolutely. If I know how a vacuum gauge works, somebody was asking me, I said a vacuum gauge works great when you do a snap test, right? Because you have the 4-inch, 24-inch. Then somebody asked, what is it if it is bad? Well, how gray is gray, right? But let's say it is a bad exhaust restriction, then it comes down to about maybe 6, and then slowly gets back up to 12 or 13. But the response isn't there. Shoo, shoo, you know. It isn't, the response is not there. Now, if you have a frequency, hey, it's the same thing. Response is what you're looking for. Do we still drop the exhaust drill holes? Absolutely not. Okay, this is the typical time event measurement. And when we set time event, we need to know when things happen. So if I want to look at any of my sensors, I would like to do this, that I take my trigger starting at somewhere up the ladder of the TPS. Not on the top, right? Somewhere, let's say at 3 volt level. I set my trigger. You see where the trigger is here? That's where my trigger point is. Well, maybe here. Because when I step on that and I look at all my sensors at the same time, then I can lock that in and go back to the shop and analyze it in one test drive. Quite often we go for a test drive by the seat of our pants without any equipment because we just want to verify that the customer was, yeah, the customer is right. There was a misfire, right? But really that doesn't tell us much. So I've researched a lot of things, and I finally found a way to look at the waveforms without getting out of the car. The worst thing that you can do is, I have a 4-channel scope. That's the best scope I can get. No, you can buy an 8-channel scope. You have less resolutions, mind you, but yeah, I could. But you know, if I have a 4-channel scope, then I can only hook 4 channels up. If one of them is a TPS, I only have 3 left. See, so what I want is more channels to put in that I can drive actually on the road and have there all my switches here. So I have here 9 outputs. When in the left position, 3 outputs here and 9 here. 9 inputs. In the left bank, I look at those 3. Next switch over, I look at those 3. Hit the space bar, lock it in. Okay, diagnose it later. Right? Then I go to the next one and I hit the space bar when it acts up. So 3 times I make it act up. Then I go back to the shop and have 9 inputs of 9 sensors. Right? My diagnoses are complete. Now, why is that so cheap? Because somebody already made that for video. See that? Okay, somebody already, I only changed that for automotive. I had to do a lot of work to make it work for automotive. Because it was, you know, basically a very flimsy unit. But if you make that sturdy and change the circuitry inside. So when I saw that, I said, man, I don't have to get out of the car because it just hangs in the window. And I can switch from one to the other. All right? So then, here we are. Here's an example of what we are talking about. Use the TPS as a reference for every sensor testing under load. Therefore, I want to go to channel A for all testing, for all on the TPS. 3 connections of my 4-channel scope, right? 3 connections on 1 channel. That leaves me therefore 6 channels left. The TPS reads the mind behind the wheel. It reports every move of acceleration or deceleration. So we connect all the A channels to the Viper terminal of the TPS. The TPS is, they call it TPS as a switch. It's not a switch. It's what we call a potentiometer. A potentiometer is a fixed resistor, right, with a Viper in the center. That's a potentiometer. A rheostat is a Viper and 1 connection. That's a rheostat. That's the difference. Potentiometer is a circuit already with current flow. So it's a voltage divider. That's basically what it is, right? That's what a TPS is. And if you use that as your standard, as your input, look what you got. Connect, let's say the tech connects any suspected sensor activated relatively, oops, there. The tech does that, okay? Relative to the customer's complaint, channel B and C. TPS 2, 3 on A channels. Program the trigger on A, and now he sends his driver out. Okay, driver, you know, you're the guy who is my helper there. You set the switch position at 1, make the car act up, and locks in the data. They repeat the same in switch position 2 and switch position 3. And then back to the shop. And now I come back there with 6 sensors, all reference made to the TPS, to the 1 input. There's my TPS, that's TPS in any position. 2 sensors, 2 more sensors. And now you do your diagnosis when you are in the shop. That's one way of doing it. All right? Now here's something that you can also consider when you do that. Whatever you do, you need longer leads. All right? Here's a practical application. The practical application is that somehow you save valuable tech time and test drive by another driver to accumulate the data. Tech can interpret the test results in the shop. We already discussed that. However, think about this. Put the switch box on the passenger side and have somebody else drive the car. And preferably have the customer drive the car. Okay? And the tech records the data and sells the job. He's now doing the diagnosis at the same time while he's driving. Because if there's nothing wrong with those sensors, go to the next one, right? Nothing and the customer said, you ask the customer, hey, you make it act up, but you said it was doing. So the customer makes it act up. You know what the interesting thing is? The payoff is that this is a first-hand experience of the customer leaves a lasting impression of professionalism. No advertising can equal the effect. And it's true. I've tried it, and it's amazing. People go to the office and they say, you know something? I was driving my car and I make it act up, and the guy was doing all kinds of funny things, and he comes out here with a shitload of things, and man, he fixed the problem. And it's something that you have to sell the customer. There's nothing better than that. Okay, the last one, use trainee as a driver. Number 1, tech collects data and diagnoses problem while on the road, while thinking out loud, making the trainee a part of the discussion. What a fabulous way of making your trainee a part of the diagnosis. We always have that obligation that we want to teach the next generation. That's our obligation. If we know something, we have to do that. That's our job, right? I'm 75 years old, and I'm still doing it, and I love it. I'm passing on what I have learned over the years. And that's what our job is in a shop too. Because you see, we deal here with other people. And the more that you train, the more that the benefit it comes to you. It comes back to you, believe me. There's not such a thing as a secret in this business. All right. Okay. You can also make a list where your sensors go. If you have a bunch of them, that you may have to do that to keep track of which lead is connected to what component. But it is A, B, and C, and it is channel 1, channel 2, channel 3. Okay? I'm going to skip this one here, and I'm going to look at the primary ignition. So then we said, look, I got the wires already there, and here when I have that the coil unplugged, that's good for when I bend over the hood and just go to the, but my problem is when I'm driving on the road. That's when it is misfiring. And I cannot just go there and sit on a fender and go drive on the load, and just try everyone out. So then we said we have the housing already, so why not putting everything that is inside of here and putting it in here. Now what is inside of here is, first of all those inputs which come from, let's say, 6 cylinders, here they are, all the 6 cylinders, they have an attenuator, 10-to-1. So I'm not burning up my lap scope. If I put 400 volts on my lap scope, poof, that's it. I did it. I should have known better. I worked with lap scope all my life. Never thought of it, right? But that's how you blow up your lap scope. So you have to have a 10-to-1 attenuator. And that's already built in. So 400 volts becomes 40 volts here. The other thing is that when I hook up to the positive side, that's not where I would get my signal. I got to go to the switching side. There are 3 wires, or 2 wires at least. Which is which? Well, try it out, and if this lights up, that's your trigger. There are your trigger lights. That tells you when there's a trigger, right? So secondly, if the wire ever falls out on the road, I know, hey, I lost my trigger, right? So I know that I'm not misdiagnosing because the cylinder is dead. Another thing that I can do now also, because I have that capability here with the switch, that I can kill cylinders. Now when you kill cylinders, you're not really killing it dead, because all what you do is you absorb the energy, which is the collapse of the field, prevent that from building up. So there is no coil output, right? That's what the kill is. So I would never see that with a current probe on my primary. So now I take my lead. It was a black lead someplace. No, that's not it. Disappeared. Oh, here it is. I stick this in here, and I can do a cylinder balance test. One cylinder, kill. The other cylinder, kill. The other cylinder, I did it on the road. While my wife on a 4-cylinder engine was driving uphill. Okay. Okay, so by killing a cylinder, you can actually feel, yes, that was contributing. Do it, very simple, very basic. Now there is another thing that is so nice about this, that I can also add to here the fuel trim generator. So if I have a condition where I see that there is one injector that's like, let's say, number 6, that is a little bit on the lean side, it looks like, now I can hook this up here, and I can add fuel to one of the cylinders. Or let's say that this one is acting up. Then I say, okay, I'm going to take the injector of this one and hook it up to this one, right? Now the injector is hooked up, I go to this one and add fuel, and I look at the scope pattern at the same time of this one. Yeah, I'm adding fuel. That means there was a lean condition. Because if I can add fuel and it increases and it clears itself, that was a lean condition. That was not a worn cam lobe, for instance. Where I can have the same scope pattern, but when it's a worn cam lobe, adding fuel is not going to help it, right? Or a restriction of any kind. It has to be a fuel-related problem. So, why is that? Why can we make it so less expensive? If I have to buy, let's say, a mold, to make a mold for this Bakelite, $40,000, but it's already made in China. All I do is I change the circuit. The same thing here. If I buy, let's say, a cable like this, okay, any harness of this type of quality, and I have that for automotive purposes, and I have that clip on one side, and that goes to the scope, it's 85 bucks. No, when you buy it in China, it's $8.50. See, so I can have the whole thing as a bundle for almost pennies. All right, let's do some diagnosis. Let's now look at the primary, because we have to know that yes, we are doing a problem. Okay, and when we're doing a problem, we can have a misfire under load. And a misfire can be caused for many reasons. However, there are two conditions that stand out as most common. One is a crossfire. And that's a common occurrence with the coil and plug ignition system for several reasons. Number one is that we can have a condition where that the plug is not easily accessible, therefore people wear the plugs out a little bit longer. Okay, the plugs wear out longer. And when they wear out longer, therefore the kV goes up, and therefore it's a lot easier to fire somewhere across the ground. Besides that, the coil is sitting in the engine, right? With ground all the way around it. Any contamination in there makes it easy to crossfire. So crossfire is very common. When I have a misfire, I need to know is the crossfire, or if it's an injector or whatever it is. So we're going to do that diagnosis. Starving is another condition. Starving under load could be an injector problem, but it can also be caused by back pressure reducing the volume, both hydrocarbon and O2. Right? We're going to look at both of them. The objective is to identify. Here's a misfire on the load. This is what I see. It is a condition that exists when kV requirement under load increases and the spark finds an easier path to ground through an insulation breakdown. So it's an insulation breakdown. How do I know? Let's look at pattern number one, at idle. This is a normal scope pattern. Engine at idle, firing time fairly linear with plenty of fuel to burn. Then at the higher speed, what do I see? I see a curve. The curve of, there comes a point where it starts to get leaner or lesser oxygen and therefore or lesser hydrocarbon. The scope sees lesser hydrocarbon as a result of lesser oxygen. So basically, at any point in this curve, the air-fuel ratio is leaner or richer. Is it leaner on the bottom or richer here? And is leaner here? It's the same. Because you see, the reason, does it make sense? The reason why we have lesser hydrocarbon, because there's also lesser oxygen. We're running out of oxygen. And that's why actually it runs out of fuel. Right? Those two are related with each other. The computer shuts off if it doesn't see oxygen, doesn't it? Computer says, hey, less fuel. Now we're burning our oxygen up. We can inhale only so much. Right? Now under compression, we are actually burning all that oxygen up, and therefore it becomes now, whoops, I'm going too far. This is on automatic. I wanted to change that. Okay? That is basically what I see. So we know that the fuel mixture is not lean. They call it a lean mixture, but it is not. Right? Lean mixture means air-fuel ratio is changed. Lesser volume, that's something different. We have lesser hydrocarbon, but also lesser oxygen. Agreed? Some are not agreeing with me. All right? Think about it. Let's go a step further. Now what happened? When the crossfire occurs, the spark sees a sudden absence of hydrocarbon. See that? Absence of hydrocarbon. Suddenly it is instantaneous, not progressive. It's not slowly getting there. It is now it happened, and now it happened, and now it don't. I back off, and it's normal. Step on it a little bit more. All I need is a little bit more kV demand, okay, here, let's say, and therefore it was easier to fire there. That is a high resistance occurring instantaneously. That is an electrical crossfire. There's a difference. Do we see this? Can we see that this happened? We see hydrocarbon as a conductor, When it is cross-firing, there's no hydrocarbon there, it's air. Right? Why does it crossfire?
Oh, okay.
Because the kV demand becomes higher under load. My kV goes up. And now the spark says, hey man, I see a better path to ground. There it is. And when it does that, what does it see? Air. Oops, I took the wrong turn. Too late.
So in the middle one, we started out with the right air-fuel ratio, okay? Then went over on the right, then clearly you didn't have the hydrocarbons, bang, all of a sudden, but it was still easier to go that way.
Right.
You're getting something.
Right.
You're getting a burn time, a burn line that looks like you don't have
Okay,
any hydrocarbons.
this is external. That's internal. There's hydrocarbon there. There's no hydrocarbon there. That's what it is saying. Okay? And that's what we want to see. Now that gives me an indication that that is indeed a problem that is an electrical problem. I need to know what my problem is before I can fix it.
So correct me if I'm wrong, so when insulation breaks down at whatever voltage level, we're gonna look at a firing line that is not really as high as it should be because the insulation broke down, but the burn line or the spark line has moved way the hell up and takes on that.
It's not higher but also shorter. See the difference?
Yeah.
See? Because there's so much energy taken here that I don't have energy left. It's all absorbed here. High resistance. It's high resistance because of the absence of hydrocarbon. It's instantaneously. Read it over and think about it some more. All I want you to do is think about it. You're getting there, guys. All right. Misfire under load. Starving is a condition that exists when one of the injectors is slightly later in becoming fully energized, either due to higher electrical or mechanical resistance. Can be both, electrical or mechanical. All right? So what do I see? A normal scope pattern here, normal there, and all of a sudden I see a misfire there. And this is almost getting there. Okay, let's analyze it for a minute. Let's look at this. No, let's look at the next one, this one. Turbulence at the end of the firing line is normal under load. See that? Resistance is rapidly increasing due to the absence of hydrocarbon as spark runs out of energy to conduct. Do we agree with that? Does it make sense? Now then, here's the next one. Hydrocarbon is breaking up but not quite bad enough to cause a misfire. First sign is increasing a nose. See that that's what we call the nose. Here that's the nose. When that increases the nose, there is still a lot of energy left, right? That finally comes back. You see the difference in oscillations? There's a lot of energy not being used by the coil because it ran out. Same thing here. Now let's have a closer look at that because that is important because you need to know why it happened. And if you know why it happened, then there is no way that you can miss it. Let's look at the duration of that firing time. What's the scope seeing? A good conductivity during the entire time of burning, right? If this is considered an adequate combustion time, then also this is considered normal. You agree with that? What about this guy? Can we see it? Can we see the third one also? What is then this? And what is this? The duration of spark, in other words, is burning that little amount and the rest of the piston is not doing anything. How much combustion can you have? That is combustion efficiency. That is combustion efficiency. That's only a quarter of this. And you see that only happens on the load. Why is it happening on the load? Because on the load, resistance has a greater effect when it's on the load, right? Resistance has a greater effect. Okay, how am I going to explain that?
So, on the two on the right, you measured the time rather than the spark line.
Okay.
Rather than the time the spark line, is that right? On the two on the right, they
Yeah.
were short.
Yeah.
You measured just the time that
This,
you
that,
know that there was a...
the time that the molecules of fuel was one molecule of fuel right next to each other, and then there was resistance, there was nothing there to burn. And there was one, and there was nothing there to burn.
Well,
Hey,
how come you didn't mark it all the way to the right, or like the peak of the nose, the end of the burn line, the spark line? How come you didn't mark that as the time?
oh, that's absolutely, that isn't time. You mean this?
Yeah,
That is burn time. So is this burn time. But it keeps on having burn time. There is conductivity there. There's no conductivity there. High resistance. Yeah, there is a molecule of fuel. No, there isn't anymore. Oh, there's nothing there to burn.
that because you ran out of fuel.
I ran out of fuel. I ran out of hydrocarbon.
I understand that.
See, it is fine, and therefore it takes more energy, and therefore the distance here is shorter than here. And if I understand that part, I understand the total idea of total ignition system. Now, how can an injector do that? Okay, let's suppose now this. Okay, let's suppose it takes time for the ejector or to overcome the spring tension or the weight of that, so more current, and finally what I see is this. Right, that's where the computer shuts it off. What is that? That's the pintle bump. The pintle bump tells me that it took all that energy to lift that plunger, all the time, that energy, and finally it's a click, there it went. Now the fuel starts to flow. Not here, there. And then did it stop flowing after this thing bounces back up to here. Now it fell back to normal. So really my time of injection time is from here to there. Now then, if I would increase my current to twice the amount of current, what will happen? I get that twice as fast. If I open up my water tap twice open, then my pail fills up twice as fast. Agreed? Right? Okay, here we go. Now we have double the current. And I get the pintle bump. Right? And my current limiting. Look at the time that I'm on now. If it is double the current, I would burn out my coil, wouldn't I? Yes, there are some race car drivers who have that. But what they do is this, hey, I'm already saturated. I don't need that much. Now let's have peak and hold. And hold is half the amount of energy. All I need is to get to the peak, and now all what the coil has to do, hold it there, don't let it go. Half the voltage. So I don't heat up my coil. Now we saw the result of a more current flow. Now I'm gonna go and do the same thing here. I have to make a new one here. Here I have my pintle bump, right? And here the computer shuts off. Now I have an injector. Instead of 13 ohm, it's 15 ohm. What does it mean? Less current. If it increases the time with more current, it decreases the time, right, with less current. Right? What happened to that injector? It turned lesser volume. Leaner. Okay. So now the time that the injector is on is less, right? From here to there rather than from there to there. And therefore that resistance is so much different, and that's why the injector under load, when the demand is great, is just that high. And that's why it is important. Let me tell you this much. And I'm not really trying to sell you on Linde technical service, but I'm going to tell you this much. That I have seen the operation of Linde when it did injectors. It's an unbelievable injector service you can never find anywhere else. Not just resistance is important, how much current flow is there, okay, and how much flow is there in total. And when you buy injectors, you have them all measured equally. And it is not so much whether it is 32 or 31 or 35, as long as they're equal. Because the computer will nicely compensate for it because of the oxygen, as long as they're equal. But if you have one injector that's bad, you replace that one. Because your scan tool told you it's misfiring. You replace it, your misfire is gone. What did you do about that one then, huh? Does that go haywire 3 weeks from now? Or are you going to replace them? Or are you going to put a brand new one in here? And now this is so much difference in there that you still have a problem. Equal is the key. Does that make sense? One new injector with 3 other injectors or 6 other injectors or 5 other injectors which are not equal is dynamite. It is unbalanced. And the computer regulates it on the average. It says all injectors are equal. Boy, they're not. They should be, but they're not after 3 or 4 years. And you know the cost of 6 injectors rebuilt is just as expensive as one brand new one. And if you get the order in, I'm selling for Gillinder maybe, but I'm not going to get a commission, but I'm such a believer in the scope. I'm such a believer in doing a good job. I'm such a believer that if you have the right tools, you can do the right job. And if the tool is sitting in a corner, it's not doing a job for you. You can have a $6,000 or an $8,000 scope and not doing the job for you. It's waste. You can buy this stuff, right, and you don't use it, it's waste. Now, if you have not much investment and you use this only once a month, it's paid for in 3 months. But on the other hand, if you have spent $6,000 or $8,000, you better use that every day, or at least enough to pay for itself in 2 or 3 years. You see, that is really the whole thing. If we understand how things work, it makes it so easy to also to do the diagnosis and do it simple. Because we're missing a lot of information that is bypassed because of the scan tool. Scan tool that says there's a misfire. Would I ever pick that out? No. This one, eventually, yes. The worst one will show up. But that one won't. Primary scope pattern is identical to the secondary. Not the spike. Okay, that is inductive kick. But the firing time is basically the same. Identical. All right? So don't say that you cannot see anything in the primary. And if the problem acts up under load, then test it under load. And if you have no way to test it under load, get some longer wires. And get the best way that you can buy them. You know, I always get clobbered about trying to sell something. No, I want you to get a better tool. I really want you to get a better tool. I want you to use that scope to the best as you possibly can. Does that make sense? Well, I hope that you've learned something. I'm out of time. I will be here around for as long as you want me to be. And I will answer all the questions. On the disk, you know, think about it. On the disk is my website. Give me a dingle. Let me know how you're making out. And if this has been a learning experience for you, tell the people in the country about it. Tell it on IATN that yes, you sat in the class and you learned something. You know, I don't have that many years more to do it. All right? Thank you very much, guys.